So in the last class, actually, we are discussing about the oblique incidence. Okay. So when you are discussing about oblique incidence, there are two types of the polarizations are there. So let us try to recollect again what all the concepts we discussed in oblique incidence. So suppose if the wave is having two planar components. So for an example, if you see in the diagram, so this is your incident wave, and this is your reflected wave, and this is my transmitted wave. So when the interface is located at z equal to 0, so which means that your perpendicular axis will be z axis. And let us say z equal to 0 is your xy plane. So as an example, consider the one which is visible for you is x axis, and the axis which is perpendicular to the plane of the paper is y axis. So if you recollect what we have discussed, if the direction of propagation has to be consisting of both x and z, if you see here, if you see the incident wave, it can be resolved as one x component and one z component. So in the same way, your reflected wave, and in the same way, your transmitted wave also. So in order to have the direction of propagation, there are two combinations are existing. So the first combination is nothing but your electric field should lies in the xz plane, keeping magnetic field is perpendicular to the plane of the paper. And the second case, your electric field lies in y direction and magnetic field lies in the xz plane. And if you recollect what we have discussed in the last class, so since your electric field lies in the same plane of incidence, or you can say your electric field is parallel to the plane of incidence, you can call this type of wave as a parallel polarized. Of course, which we are supposed to discuss right now. And in the last class, we have seen this electric field in this case is perpendicular to your plane of incidence. So that is the reason why we are calling it as a perpendicular polarized. And when it is perpendicularly polarized, we already defined what happens to be the boundary conditions and the reflection coefficient and the transmission coefficient. So all the equations has been given, right? So then now we'll see the parallel polarized. Okay, now when you see the parallel polarized, what is the condition I told you? Your electric field should lies in the xz plane and your magnetic field should be in y direction. The same thing you can see here. So if you see this incident electric field, you can resolve one component along the x-axis, one component along the z-axis. Okay, so let me represent something like this. This is my x-axis and this is my z-axis. I assume that y direction is perpendicular to the plane of the paper. Can you tell me how this incident electric field can be resolved? So this incident electric field can be resolved into how many components? So what is this component and what is this component? Which means that you can resolve along positive x and you can resolve along positive z. So anybody is having question here? So this is very important. You have to understand how you have to resolve the incident electric field vector. So that will be along one positive x, you can see here, and one positive z. I want everybody to post the answer here. When you resolve this reflected electric field component, what all the component will come after resolving? So when you're resolving ER, what all the components will be present? Quickly. Negative x and positive z. Very good. Yes. This will be resolved like this, which will be your negative x, and this will be resolved like this, which will be your positive z. Very good. Similarly, can you tell me about ET? What is the transmitted electric field? How it will be resolved? Positive x and positive z. Very good. This is your positive x and this is your positive z. Very good. Correct. So I hope you are familiar with that. Now, in the same way, can you tell me the direction of propagation? So if you see this, this is your direction of propagation. How will you resolve the direction of propagation for the incident wave? Have a look on the direction of propagation. Till now we have seen only the incident electric field. I'm not going to ask that. So if you see the direction of propagation, this is the way how the wave is propagating. So if you resolve this component, just reply what all the components will be present. Positive x and negative z, very good. They like this, positive x and negative z, very good. So similarly, can you tell me for reflected wave? This is your reflected wave. Can you resolve it? I want everybody to answer. How to resolve this component? This is your positive x and positive z. Agree? This is your positive x and positive z. Yeah, good. And what about your transmitted wave, the direction of propagation? Good. Positive x and negative z. That's it. If you're understanding this much means you will be able to solve the problem. The rest of the things are just only the simple mathematical equations. As I said you, if you understand how to resolve the components, the problem is easily simplified. Whatever the problem it is, complex problem. Okay. Okay, then we'll go ahead. So in the parallel polarized, your electric field lies in the x plane and magnetic field is in y direction. So what is the first boundary condition? When any signal enters from medium 1 to medium 2, the tangential component remains same. So that is nothing but your E tan 1 is equals to E tan 2. So how to resolve E tan 1 here right now? See here, this is the tangential component for the incident electric field. And this is the tangential component for reflected electric field. Now, if I say E tan 1, that is nothing but the incident electric field tangential component minus the reflected electric field tangential component. I hope you would have been understood why I have included minus here. If you see here, this tangential component and this tangential component are moving in opposite directions. So that is the reason why the net tangential component is the difference of the tangential component of incident field and the tangential component of the reflected field is equals to E tan 2. So you can see here E tan 2 means this is your E tan 2 in the medium 2. So that is the tangential component of the transmitted electric field, Et tan 2. So in the last class you have remembered, I think, how to resolve this tangential component. Anybody? If we have this resultant vector, what is this angle? You go through the previous discussion. We already know this is your 90 degrees and this is your 90 minus theta and this is nothing but your theta. So what happens to this tangential component was, since it is adjacent, you are going to get hypotenuse times, hypotenuse is nothing but EI, which is the very good, EI into theta minus. Similarly, this is also same thing. Once if you find out for one thing, everything follows the same pattern. So ER tan 1 is nothing but ER into cos theta is equals to, so this can be written as the resultant times ET into cos theta t. Okay. So what will happen? EI minus ER is equals to ET into cos theta t divided by cos theta I. So this is your first equation. And similarly, when you are resolving the magnetic field component, you are having tan 1 is equals to H tan 2. As I said, your magnetic field is in y direction. So y direction is lies along the surface only because your interface is located at z equal to 0. So when you have your z equal to 0 plane, your x-axis will be tangential and y-axis also will be tangential. So your HI and HR both lies in the y direction, right? Similarly, HT also lies in the y direction. When you see the medium one, so the total tangential component is nothing but your HI plus HR. And the total tangential component in medium 2 is equal to HT. So this is by assuming that there is no surface current on the interface. So I can say H plus R is equals to HT. So this also can be written as EI by eta 1 plus EI eta 1 is equal to ET by eta 2. Just replace the magnetic field in terms of electric field. So what is the equations you are going to get? EICR is equals to ET into eta 1 by eta 2. So this is your second equation. Okay. So just take some time and tell me what is the value of reflection coefficient you are getting and transmission coefficient. So quickly do the calculations. You are having the two equations and do 1 plus 2 and 1 minus 2. So you are going to get the reflection coefficient, the transmission coefficient. So please do that, and once you are done with that, you just let me know. The equations here, you can verify it later. Will it be fine? Is that fine if I write the equations here? Because you need not to memorize these equations. As I said in the last class, I was going to give a shortcut if you want to solve the problem. So straight away I will write the equations here, and soon after the class you can just verify whether it is correct or not. Okay. The only intention here is just you need to understand what is the approach I was following. Okay. So I will write the equations here. So you are going to get the reflection coefficient as eta 2 cos theta t minus eta 1 cos theta I by eta 2 cos theta t plus eta 1 cos theta I. So what you got for the S polarized, there you are having secant. And in this case, you are going to get cosine. That is the only difference. And similarly, the transmission coefficient you are going to this equal to eta 2 cos theta I by eta 2 cos theta t plus eta 1 cos theta I. So these are the equations for your reflection coefficient and transmission coefficient. But you need not to memorize these equations. You need not to worry about these equations. Okay. Do you have any questions to ask here related to S polarized and P polarized? So the summary is here. The S polarized is also said to be the perpendicularly polarized. So in that case, your electric field lies in y direction and magnetic field lies in XZ plane.
Sir, tau will be 2 eta 2 cos theta I or cos theta t?
It is cos theta I. You can verify it because if you compare with the S polarized, there actually 2 eta 2 secant theta t is there, right?
Yes, sir.
Yeah. Here you just verify. It will be cos theta I.
Okay, sir.
Yeah. You can verify it. No problem. And for S polarized, your direction of propagation is in XZ plane. And similarly, this is a P polarized or parallel polarized. So your electric field lies in the XZ plane and your magnetic field lies in the Y direction. So again, the direction of propagation is in XZ plane. So this is so you have any questions at this moment, or shall I go ahead? Okay, then we'll go ahead now. So, and finally, we'll come to the end of the second chapter, wave propagation, by discussing the critical angle and the Brewster angle. So, have you seen the critical angle anywhere? So, in which topic you would have been seeing this critical angle? Total internal reflection. Very good, very good. And basically, you have seen this kind of critical angle concept in optical fibers, right? So, whereas when you see an optical fiber, what will happen? There is a core and which is surrounded by the cladding. So if any signal is incidenting within the core, the wave cannot enter into the cladding medium. So the wave will get reflected back. So this process, you are calling it as a total internal reflection. So first of all, what do you mean by that critical angle was? See here, suppose this is your interface and this is your medium 1 and this is your medium 2. Okay, when any signal is incidenting on the interface with an angle of theta I. So what does it mean? If the angle of incident is equal to critical angle, whatever the total there should not be any transmitted wave into the next medium. If the angle of incidence is exactly equal to the critical angle, there should not be any transmitted wave, which means that everything will be reflected back into the same medium. So the critical angle can be defined as the minimum angle of incidence for which there will not be any transmitted wave. So which means that your full wave should be reflected back into the same medium. Do you have any question here? And what will happen when the angle of incidence is greater than critical angle? So the critical angle is the starting minimum angle of the minimum angle of the incidence for which there will not be any transmitted wave. Suppose consider the case where your angle of incidence is more than critical angle. What will happen? Do you think in that case total reflection takes place or total transmission takes place? Good. So for total internal reflection or total reflection, it should happen, which means your angle of incidence should be greater than your critical angle. Okay. So for critical angle to exist, so as I said, it doesn't have any transmitted wave, right? So critical angle says the full wave should get reflected back into the same medium. So when the wave is getting back into the same medium, there will not be any transmitted wave. So in such case, I can say for critical angle to exist, the transmission coefficient must be equal to 0. Will you agree with me? If I say the angle of incidence is equal to critical angle, I can equate my transmission coefficient will be equal to 0. Does that make any sense? Is it correct or not? Yeah. When I say any critical angle, as per the statement is concerned, there will not be any transmission. So whenever there is no transmission into the second medium, you can equate the transmission coefficient straight away equal to 0. So what you can do right now, you can take it as an assignment I was giving. So you know the equation for S polarized, what is the transmission coefficient? And you know the equation for P polarized also. What is the transmission coefficient? You just equate it to 0 and find out what is the angle of incidence. So that is nothing but your critical angle only. So you are going to get this equation. So theta C, you are going to get sine inverse root of epsilon R2 by epsilon R1. If you consider both the mediums are ideal dielectric. Do you have any questions here? You have the equations for transmission coefficient for both S polarized and P polarized. You just equate it to 0 and find out what is the value of theta I. There is a question, sir, is theta I greater than equal to theta C for complete reflection? Correct. So your angle of incidence has to be greater than your critical angle for the total reflection to take place. Okay, this is a mathematical part. You can verify it later. I will give an example here. Okay, this is my interface. Let us say this is my angle of incidence. And suppose if the reflected wave is grazing the interface, can you call this angle of incidence as a critical angle in that case? So there is a particular angle of incidence where my reflected wave is just grazing over the interface. Can I call that as a critical angle or not, as per the definition? Yes, very good. So in such case, what is the value of theta t here? Your theta t becomes 90 degrees. So because I can call this as a critical angle because there is no wave which is propagating in the second medium. What will happen if we still increase the angle of incidence? This component is going to become like this. Suppose if you are pulling this angle of incidence with a more angle, your reflection will be confined only to the medium one. And suppose still if you are increasing more angle of incidence, it will be fully confined to the first medium only. So if you want to find out the critical angle, that should be the minimum angle of incidence. So I can say the angle of incidence is equal to critical angle when your theta t is equal to 90 degrees. So if the angle of incidence is more than critical angle, your wave is completely restricted to the first medium. So if you see the Snell's law, I have given there one equation. If you have two different mediums, I have given sine theta I by sine theta t is equal to root over epsilon r2 by epsilon r1. So now in this case, what will happen? Your theta is same as your critical angle and theta t is 90 degrees here. So you can substitute that. What you are going to get? So sine theta c is equal to root epsilon r2 by epsilon r1. So theta c is equal to sine inverse root over epsilon r2 by epsilon r1. So this is the formula for your critical angle. So either you can go in a mathematics way and just equate the transmission coefficient to 0. You will get the same equation. Or otherwise, I was telling an other alternative approach where you can equate your theta t equal to 90 degrees. So that time the angle of incidence is also said to be the critical angle. So any questions here? So do you have any questions? Yeah. And one more here, there is a very interesting thing. So you know that from this equation, I can say sine theta c is equal to root over epsilon r2 by epsilon r1. You know the maximum value of sine theta will be exactly lies from 0 to 1 if you take the modulus. So when you take the magnitude, it will be anyhow lesser than 1. So what will happen in that case? Your root epsilon r2 should be lesser than root epsilon r1. So which means your epsilon r1 should be greater than epsilon r2. So this equation says, in order to have the critical angle, the first medium permittivity should be higher and the second medium permittivity should be lower. So which means the wave should enter from denser medium to rarer medium. So the critical angle is only possible provided the incident medium should have more permittivity and the transmitted medium should have the lesser permittivity, which means that the wave is propagating from denser to rarer. That is the same thing you can see in the optical fiber. In optical fiber, you are having a core surrounded by the cladding. So what will happen when any signal is incidenting within the core? The reason being why it is getting reflected back was the permittivity of the core is higher than the permittivity of the cladding. So because of that, you are having a critical angle. So whatever the angle of incidence at this point will be more a critical angle. So that time the wave is confined to the first medium. Cladding is dielectric. Yes, it is a cladding is also a dielectric. It is really made up of glass in an optical fiber. Both are a composition of glass only with different refractive index. Yeah. Then we'll go to the next one, Brewster angle. So Brewster angle is quite opposite to the critical angle. So when I say for the critical angle to exist, your transmission coefficient has to be 0, which means that the wave should be completely reflected. Brewster is the opposite. So when any signal is incidenting on any interface, the signal has to get transmitted. So in other words, I can say for Brewster angle to exist, there should not be any reflected wave. So for Brewster angle to exist, there is no reflected wave. So what is the condition in such case? So for Brewster angle to exist, if there is no reflected wave means you can equate the reflection coefficient is to 0. Okay. This is your medium 1 and this is your medium 2. So when the angle of incidence is equal to the Brewster angle, the complete wave is getting transmitted into the second medium and you will not have any reflection in the first. So this angle of incidence is said to be the Brewster angle. So for Brewster angle to exist, your reflection coefficient has to be equated to 0. Okay, I will come to the S polarized separately. First, I will see what will happen when you equate for P polarized. So what is the reflection coefficient I given? Just now we have solved that. Eta 2 cos theta t minus eta 1 cos theta I by eta 2 cos theta t plus eta 1 cos theta I is equal to 0. So for P polarized wave, if the Brewster angle has to exist, your gamma has to become equal to 0. Okay, now once you proceed it here, so what happens? Eta 2 cos theta t minus eta 1 cos theta I is equal to 0. Okay, now in this case, what will happen? Eta 2 by eta is equal to cos theta I by cos theta t. Okay, what you can do the simple manipulation, something like, you know that eta 2 is nothing but 120 pi by root over epsilon r2 if it is a dielectric medium. And eta 1 is equal to 120 pi by root epsilon r1. So what will happen? Eta 2 by eta 1, you are going to root epsilon r1 by epsilon 2. So I can substitute here. And the same thing, so cos theta I can also be written as 1 minus sine square theta I divided by 1 minus sine square theta t. I think you already know, right? So sine theta I by sine theta t is equal to root epsilon r by epsilon r. So what you do, you replace sine theta I in terms of epsilon, and going further, you are going into relation for this. So for Brewster angle to exist, you will get the angle of theta I. You are going to get tan theta b is equal to root over epsilon r2 by epsilon r1. This is the equation you are going to get. So once again, I was repeating, whoever has not understood, for p polarized wave or the parallel polarized wave, if the Brewster angle has to exist means your reflection coefficient has to be equated to 0. So when you equate the reflection coefficient equal to 0 and proceed further, all these mathematical things and all, you need not to do that. Just remember, so after equating this one, and if you replace theta t in terms of theta I, so what is the angle of incidence you are going to get is nothing but tan inverse root over epsilon r2 by epsilon r1. So this is the formula for the Brewster angle. So you want me to explain it, or will you do? So this exercise you have to do it by the next class. So just equate this one equal to 0 and you can replace sine theta t with sine theta I into root epsilon r1 by epsilon r2. And you can find out what is the value of theta I you are going to get. So you are going to get, this is your Brewster angle equation. So will you do? Good. Okay. You can do that, but the final point, anyhow, I was going to share the presentation to you, right? In that all the derivation part is there. If any doubt is there, you can go through that. That is not an issue. So this is the formula for your Brewster angle. Now what will happen when you equate for S polarized? This is very important. So when you have your S polarized, if you recollect, the gamma equation has been given like this. Eta 2 secant theta t minus eta 1 secant theta I by eta 2 secant theta t plus eta 1 secant theta I is equal to 0. And you proceed in the same manner that what you have done for the p polarized, you will get end up with epsilon r1 is equal to epsilon r2. So what is the meaning of that? For S polarized wave, if the Brewster angle has to exist, means you are going to get the conclusion finally epsilon r1 is equal to epsilon r2. Will it be happen in reality? If the wave incidenting from one medium to other medium, can you expect the permittivity will remain same? Especially when I am talking about dielectrics. Can you have same permittivity for two different mediums? Absolutely not. So that is the reason why mathematically, if I can explain, for S polarized wave, the Brewster angle cannot possible, because for S polarized wave, if you assume that your reflection coefficient is 0, mathematically it represents the permittivity has to be equal for both the mediums. So which cannot be happen in real case. So when you have two different dielectric medium, means your permittivity has to be different. So that is the reason why this is a very, very important point you have to remember. So the Brewster angle is not possible for S polarized wave or perpendicular polarized wave. And the Brewster angle is possible only for the P polarized wave, and the value of Brewster angle is given by this equation. So do you have any questions here? Yeah. So this is actually the conclusion for the second chapter, that is the wave propagation. So with that, we have all the concepts, whatever is there in the wave propagation. So if you recollect what we have started and where we have started, and we started with the time varying Maxwell equations, then we have arrived at the wave equations, and we have discussed a special type of wave called transverse electromagnetic wave, and we have find the solution for that TEM wave when it is propagating in a lossless mediums. And then we have defined all the constant like propagation constant, phase velocity, intrinsic impedance. And then we come to the concept of polarization, and there we have seen after that actually we have seen the reflection for the normal incidence and as well as for the oblique incidence. So and finally we ended up with the critical angle and Brewster angle. So this is what actually the summary what we have discussed in the second chapter. Okay, so before going to the problems, if you have any doubts, so please clarify. If you have any doubts, let it be, you can ask me, I will be able to.
Sir, when we have
Yes.
something like electric field given, both X and Y components are there.
Okay.
How to find beta in that case? Like
How to
phase,
find?
beta or phase, or that the angle.
What angle it is?
For
No, it is a
example,
simple. No, I got your point. Suppose if the wave is propagating in this direction. So suppose if we know the resultant propagation constant, okay. So let me consider an example. So this is my x-axis, okay, and this is my z-axis, and the wave is propagating in this particular direction.
yes,
So
sir.
this direction, this is your resultant propagation.
Yes,
Okay. Now, how to resolve this propagation constant? One component along positive x, one component along negative z. Agree?
yes, sir.
How to find out the propagation constant along x direction and z direction? That is what your question, right?
Yes, sir.
Yeah. Now you know the angle of incidence, right?
Yes, sir.
And this is your 90s, and this is your beta. Okay. You can see this triangle.
Yes, sir.
So what will happen? This is beta x, and the resultant value is beta, and this is nothing but your theta. Now, are you able to find out? This is your beta z, right?
Yes, sir.
This is your beta z. Yeah. Now you can apply the sine theta, right? So sine theta is equal to beta x divided by beta. So the beta x can be resolved as resultant times sine of theta. You got my point?
Yes, sir.
Yeah. Similarly, beta z can be written as resultant times cosine of theta.
Okay, sir.
Okay. Yeah, any other questions apart from this? Okay, we'll start with the problems first. So read the question. So there is a uniform plane wave in air impinges at an angle of 45 degrees on a lossless dielectric medium with dielectric constant equal to epsilon r. Given the transmitted wave propagates in 60 degrees with respect to the interface, and then find the value of epsilon r. So there is an interface located here. You can read the statement clearly. And the wave propagates from free space. First medium is free space, and the second medium is the dielectric. So here he has given the wave impinges at an angle of 45 degrees. Okay, let us consider this is your normal 45 degrees. And then the transmitted wave makes an angle of 60 degrees with respect to interface. So first, can you tell me what is the value of theta I and theta t? By reading the statement, what is the angle of incidence here? 45 degrees. Angle of transmission is equal to 30 degrees. Very good. Correct. Because you can see here I have given the angle is 60 degrees with respect to interface. But you remember, as per the Snell's law, the angle of incidence, reflection and transmission should always be measured with respect to normal. Right? If it is 60 degrees with respect to interface means 30 degrees with respect to normal. So this is your theta I and this is your theta t. So you have the Snell's law, right? You can find out that. So what is the formula given? Sin theta I divided by sin theta t is equal to root over epsilon r2 by epsilon r1. So all the values are given. So can you tell me what is the value of epsilon r then? So the first medium epsilon r will be 1 because it is free space. So find out epsilon r2. So simplify it and share the answer once you are done with that. So 1.5. So verified. Huh? So that is 1 by root 2 by 1 by 2 is equal to root epsilon r2. Is it 1.5 or something? So root epsilon r2 is equal to root 2. Yeah, fine. So you are going to get 2. Please cross check your answer. Okay. So we'll go to the next problem then. Yeah, this is a kind of problems very important. The statement looks to be very, what I mean to say, it looks to be very lengthy question, but the answer is very simple. So first of all, everybody I was asking, have a look on the diagram. Have a look on the diagram and what type of polarization it is. Is it parallel polarized or perpendicular polarized? Others also let them reply. Perpendicular. No, it is parallel polarized. Just now we have seen. Even in the diagram also you can see here, the direction of propagation lies in the XZ plane. You can see here. And the electric field also lies in the XZ plane. So since your electric field lies in the same plane of incidence, that is said to be parallelly polarized. Yeah. Now in this case, what is the question he has given? So the wave, whichever is propagating, is having a wavelength 600 micrometer. Is propagating in a direction as shown below. So this is your incident wave and this is your reflected wave and this is your transmitted wave. So first find the angle of incidence. So can you tell me how to find the angle of incidence? This is your angle of incidence theta I and the transmitted angle is 19.2. So you can apply the Snell's law. So what is that? Sin theta I by sin theta t is equal to root epsilon r2 divided by epsilon r1. So can you do and tell me the value now? So sine theta I divided by sine theta t will be equal to 19.2 degrees is equal to root over epsilon r2 is 4.5 and epsilon r1 is 1.0. So from this, all of you try and tell me what is the value of theta I you are going to get approximately. So do it, everybody. So once you are done with that, you can just let me know. I will verify the answer. Correct. It is to 45 degrees, right? Everybody try later. You are going to get a value of theta I is equal to 45 degrees. So the option is going to be either B or C. So option A and D are ruled out. You need not to C. So can you guess what is the option right now, at least? So option A and D are ruled out. You just see the options B and C. Can you guess what is the option it can be? Anybody? Out of option B and C, which one do you think is the correct answer? He is asking to find out the expression for incident electric field. Option C. Very good. See here, it is very simple. When you see the option B, here you can see the direction of, by seeing the option B, what is the direction of propagation? Just have a look on option B, and by seeing this, what is the direction of propagation here? Z. But actually, what is the direction of propagation? If you see the actual direction of propagation, it consists of two components. So can you tell me what are those two components? So this is your incident wave. So this is your propagation direction, right? So when you see the propagation direction, this is having this component and this component. Yeah, good. One component along X and one component along Z. So when you have positive X and positive Z, what it will reflect in the propagation? Negative X and negative Z. So if you see the option C, what you are having a negative X and you are having a negative Z. So that is satisfied, correct? So everybody understood what I'm saying? So when you resolve the propagation direction, you will get one positive X component and one positive Z component. So which means that till now what is the theory says, whatever you are having in the propagation direction, in the phase part, it will be exactly opposite. So here you are having positive X and positive Z. So it should reflect negative X and negative Z in the options. So option C is correct. And even if you are having the doubt, you verify the magnitude of electric field also. Okay, you are finding the expression for incident electric field. So what happened? You have seen what is the direction of propagation, but how to resolve this vector right now? So everybody answer. What is the resultant components this EI is having? So if you resolve EI, what are the components you are going to get? Good. One component is X and this will be negative Z. Now in this case, it is not opposite because this is your electric field. So if it is propagation direction, then only in the phase term you are going to get opposite. But when it comes to the magnitude of electric field intensity, it remains same. So which means that it is having X component as well as negative Z. So you can see the options. This is having X component positive and Z component negative. So everybody understood how to solve this problem now? This kind of problems. The first thing, resolve the direction of propagation. So whatever it comes here, when you look at the phase part, it will be exactly opposite. That is the first verification. The second verification was resolve the electric field itself. So whatever the components you are having, so that should be as it is present in the magnitude part. So in this case, the propagation is having positive X and positive Z. So when you look at the phase part, it should be opposite. So which means you are negative x and negative z. And similarly, when you resolve the incident electric field, it is having positive x and negative z. So using verification, it should be the same way. One should be positive, the z should be negative. So option C is correct. So do you have any question now in this problem? Shall I go ahead? You can reply. Whether you understood or not, at least you can reply so that I can get the feedback. Yeah. So you see the same problem. In the previous problem, you find the expression for ER. So you find the expression for ER. Okay, in the same problem, first you can see here, when you see the reflected electric field component, and this is your propagation. So everybody reply, what all the components the propagation direction consists of? So when you see the reflected wave propagating in this direction, what all the components it is having? It is having positive x and negative z, correct? Okay, in that case, what it should reflect in the phase part? So when you look at the phase part, what it should reflect? So since it is positive x and negative z, it should reflect negative x and positive z. So have a look on the options. You should have negative x and positive z in the phase part, because your direction of propagation is having positive x and negative z, but in the phase term it is exactly opposite. You should have negative x and positive z. So what all the options are satisfying here? Can you reply? Option A and C. So you can see here option A and option C. So negative x and positive z. So option B is ruled out and option D is ruled out. So what you are going to verify right now? So out of option A and C, the answer you are going to get if you resolve the reflected electric field. Okay. So come back here. So when you resolve this particular component, can you tell me what all the component exists? So take this ER, how this ER vector can be resolved? What all the components it is having? Negative x and negative z. Very good. Negative x and negative z. So you can see the options right now. So it is as it is right now. So when you see the ER vector, you should have negative x and negative z. So what is option satisfying? Everybody? This is a tricky question. So which option is satisfying? Option C. Good. Can you tell me how it is option C? Anybody? You can turn on your microphone, at least one person. And can you tell me how option C is satisfying?
So because x and like it was x negative x negative y x and
But here
y.
both are positive x and positive z. Then?
So but that was the only option with same sign.
Correct. But the thing is actually, see here, the reflection coefficient, you know, right? ER by EI is basically said to be the reflection coefficient. So what you are going to have, ER is equal to the reflection coefficient times EI. Okay. Now what you are going to have, ER, you are going to have negative X and negative Z. Okay. But if you see the options, option A is ruled out because it should be having both same sign, either negative X or negative Z. If you see the option A, one is positive X and one is negative Z. That will not happen. Why? Because even in this case also, negative X and negative Z is there. But still I can say option C is correct because your reflection coefficient can become negative. So suppose if your reflection coefficient is becoming minus 0.23, what will happen in that case? That minus and this minus get cancelled. So minus 0.23 into minus of x plus z, your minus gets cancelled. So everybody understood what I meant to say? So option C can be correct if your reflection coefficient is going to be negative. So you understood what I'm saying?
So,
Yeah.
what if they give like one option with minus and one option with plus?
Which one? Which one?
As in minus.
No, here AX minus AZ. This option or which one you are talking about?
No. So, like in C, like just like C, if
there is
one
one more
option
option.
is
Something like this. Yeah, I will write like this. Just to confuse you, I will write this equation. Okay.
yes, sir.
In that case, there is no option. Through verification, you cannot do. What you have to do was, I have given the equation for the parallel polarized, right? That is eta 2 cos theta t minus eta 1 cos theta I. That equation is there, right?
Yes, sir.
Yeah. In this case, you know what is the value of theta t and theta I, and you know what is the impedance of both the media. Then you can find out what is the value of gamma you are getting. So that till now that kind of problems has not been given, because as I said, right, GATE is always testing your aptitude skills rather than memorizing the formulas. Okay. So if suppose if the person like me, whoever is giving the preparing the question paper means, so what I mean to test was, I need to test what is your understanding level. So suppose if I give the same option C and D just by changing the sign, I don't think anybody will be able to do that, because we can't memorize the equations, right? So suppose if any person is doing like this means you have to go it in a conventional classical way. So you should memorize what is the equation for the reflection coefficient, and you know the value of theta t and theta I, then find what is the value of gamma it is coming. So am I answered what you
Okay. Yes,
am I
sir.
answered
Yes,
to your
sir.
question? Yeah.
Yes, sir. Yes. Thank you.
Yeah. So like this kind of problems are getting, but you need not to worry. Till now, whatever the questions they have asked in oblique incidence, all the questions you can easily verify through, all the question can be solved through verification. So that is the reason why at the starting point only I said, you need not to memorize any equations. Just you have to be comfortable with how to resolve the components. That's it. And it is actually more advantageous if you are very comfortable with this topic, because most of the students, they will be afraid when it comes to the oblique incidence. I hope I made the concept somewhat easier. Okay, and once again you go through that concepts also, and if you are able to memorize it, it is well and good. If you are not able to memorize also, I have given an approach how to solve the problem. Okay, so any other questions you are having other than that? Okay, that is the conclude. With this, actually, I was concluding the second part, wave propagation. So if you have any questions, we can discuss right now. And actually, even in the assignment also, I have given a couple of questions related to the oblique incidence. There you can find out how to solve this type of questions. So anything you want me to discuss right now in the wave propagation, we are ready to do. Yeah.
So actually, I was like the S polarized and the perpendicular polarized was not very clear for me. So,
Okay. Okay.
could you explain it here now or later towards the end of the class?
No. Since we are in the same topic, it's better. You can easily understand now. Okay. So anybody, not only for you, others also, you can just listen what I was saying for S polarized and P polarized. So the thing was, when I was talking about S polarized and P polarized, I have considered one case where the plane of incidence is in the XZ plane. So which means the wave propagates in a XZ plane. So see here, suppose this is your direction of propagation. I should have one X component and one Z component. So if I want to have the direction of propagation in both X and Z, there are only two cases possible. So in the first case, your electric field should be in XZ plane, and magnetic field is in y direction. So what will happen in this case? Your x cross y, you are going to get one z component, and z cross y, you are going to get one x component. So it is satisfied, right? So similarly, what is the possibility of the next one? Your electric field lies in y plane and magnetic field lies in xz plane. So this is your second possibility. So whatever I was talking about S polarized or perpendicular polarized, if you see here, what do you mean by polarized? Polarization is always meant for electric fields. So how the electric field is oriented, that basically defines the type of polarization. So if you see the first case, the electric field is polarized in xz plane. Okay, and even your direction of propagation is also in xz plane. So which means that, so your electric field is parallel to the plane of incidence. So your plane of incidence and your electric field both lies in the same plane. So which can be said to be a coplanar. So that is the reason why the first case is basically said to be the parallel polarized. So parallel is also stands for p polarized. Actually p stands for polarized parallel here. So that what I hope it is clear, parallel polarized. Now when it comes to the second case, so your electric field lies in the y plane. But actually what is your plane of incidence? The plane of incidence is there in xz plane. So how this electric field is oriented with respect to plane of incidence? So can you answer? When you see the second question, your electric field, your electric field is oriented perpendicular to the plane of incidence. So that is the reason why I was calling it as a perpendicular polarized. Okay, and what that S represents there, actually speaking, S, if you see the textbook, there is nowhere mentioned it is what is actually S stands for, but my understanding, I was sharing it to you. S actually stands for the surface polarized, which means that, so as I said when I was discussing about S polarized, the interface is located at Z equal to 0. So Z equal to 0 is your plane, so the perpendicular direction is Z. And this surface is having two components, right? This is along X, which you are able to see, and this is nothing but your Y. So in the second case, whatever I was talking about second case, the electric field is perpendicular to plane of incidence. That means if you see the direction of propagation, your electric field is there in Y direction. So what you mean to say? It is perpendicular to the plane of incidence. That is the reason why it is said to be perpendicular polarized. But at the same time, your electric field is lying along the surface. Along the surface means this interface. Is it correct or not? So wherever the interface is located, in the second case, this electric field is located along the surface. So that S stands for surface polarized. Of course, it is perpendicular to the direction of propagation, but still it lies along the surface. So when you are talking about interface, that is lies along the surface, and when you are talking about direction of propagation, it is perpendicular. So is it clear? Yeah, okay. So other than that, any other questions you will have? Yeah. So how many of you have solved the assignment problem? So do you have any question in the assignment problems you can discuss right now before going to the transmission lines?
Number 10, sir. Assignment number, question number 10.
So everybody, you just open the assignment. So whatever the doubts you are having, I will be able to explain. Okay. Just give me a minute. I was opening that presentation. Yeah. See the 10th problem, everyone. So assume that there is a plane wave in air with an electric field intensity, he has given this value. √3z into A cap is incident on a non-magnetic dielectric slab of permittivity is equal to 3, which covers a region z greater than 0. Then what is the angle of transmission in the dielectric slab? Okay, fine. So to find out the angle of transmission, you need to find out what is the angle of incidence. Correct? So the wave is entering like this. And let us say this is the normal. And this is your transmitted wave. So I can define this as theta t. And this is nothing but my theta I. Okay. And can you tell me what is the resultant propagation direction here, beta? Yeah.
Sir,
Can you tell me what is the resultant propagation direction? I mean, the wave is propagating in the positive x and positive z. So calculating the resultant value of beta. So what is the value of resultant beta? So this is a propagation constant along x direction, and this is a propagation constant along z. Agree?
Yes, sir.
Yeah. So beta x value is equal to 3 and beta z value is equal to √3. So what is the resultant value right now? Beta.
So we can do the
So
square directly.
whenever you are taking in terms of vector, you should take square root of sum of the squares. You should not directly add, right? That you would have been known in vectors, right? So beta is equal to beta x square plus beta z square. So what is the value you are getting? Can you simplify?
So √12, sir.
So √9 divided plus 3, √12. √12 means I can write it as 2 √3.
Yes, sir.
Yeah. Now, using this diagram, you can see here, this is your beta. So beta can be resolved along, this is your z equal to 0 interface. So z equal to 0 interface means the perpendicular axis is z. And the interface is having xy plane. So let me call this as my x-axis. And y-axis is something perpendicular to the board. So when I resolve this component, what is this constant? This one said to be? So this is your resultant propagation. I can say this component represents the propagation constant along x direction. Agree?
Yes,
Because you
sir.
can see here, this is my x direction. Agree?
Yes, sir.
Hello?
Yes, sir. Yes, sir.
You can see here, this is I can resolve this beta along x direction as well as the z direction. Okay. This is my beta z. Okay. So what is the condition you can say from that? By seeing the triangle, you can see this right angle triangle. So how to write the value of beta x? Beta x can be written as beta times sine of theta because it is
Yes.
opposite. Agree?
Yes, sir.
So what is the value of sine theta in that case? Beta x divided by beta.
Okay. Yes, sir.
So you know the beta x value is equal to 3 and resultant beta will be 2 √3. So what is the value you are going to get? √3 by 2. Agree?
Yes, sir.
Now you can use the Snell's law, right? So what is the Snell's law says? Sine theta I by sine theta t is equal to root epsilon r2 by epsilon r1.
Yes, sir.
Okay, sine theta I value straight away you are getting the value √3 by 2 divided by sine theta t is which you are supposed to find out.
Yes, sir.
Is equal to root of epsilon r2 value is given 3 and first medium is free space.
Okay.
So what you are going to get in that case? So sine theta t is equal to 1 by 2. So your theta t becomes 30 degrees. Correct?
Yes, sir.
Yeah. Yeah. Any questions here you are having other than that?
No. Okay, if we get like this, then we have to draw and we have to find the resultant only.
Exactly. What actually required, right? Because if it is proper, if the wave propagates in one direction means it's quite simple.
Yes, sir.
Okay. So when you are having two components, because most of if you see the problems, it will consist of more than one component. So you have to draw and you have to analyze. Actually, these are the cases only actually test your understanding. That's what, right? The moment your visualization has to be more clear here. Right now, whatever the statement you have read, how efficiently you are putting it in a diagram and then analyzing. That's what actually get tests. So suppose if I give any problem straight away, based on memory based, it is not going to, it's not the correct way I felt. So this kind of problems actually test how much you have understood. And in such case, your memory power can also, sometimes it may not be required. So that's what I felt. Yeah. So next one is the sixth question. Yeah, just go, let me open that. Yeah. Sixth question, what is the problem? Anybody done? What is the sixth question answer? Can you post? Whoever has done.
I'm getting A, sir.
Lossy dielectric of permittivity greater than 1. Yeah, good. You can see here by seeing this, you can find out the phase velocity, right? So the phase velocity, what is the value you are getting? So 10 power 8 divided by 3. Okay. So because if you see the options, all the options has been given in terms of dielectric. So in case of dielectric, what is the phase velocity? That will be C divided by root over epsilon r. Assume that the option is dielectric, and I was finding out what is the value of epsilon r. Okay. Then what will happen? Root epsilon r equal to 9 and epsilon r is equal to 81, which means much higher than 1. So whatever the formula you have used, this is satisfied for the lossless dielectric. And at the same time, you are getting epsilon r value will be greater than 1. So option A is correct, right? But it can't be lossy dielectric because just have a look on the equation. What kind of medium we can say?
Lossless.
Yeah, because you can see the magnitude is a constant. Okay, any other questions apart from that? Okay, then still anyhow, if you have any other questions, you just practice it. And if you are not able to do, you just share it in the group so that I can give an explanation for that. Okay, then one thing you can do, you can sign out now and we'll make a one fresh session based on the transmission lines. All of you can sign out and I will start a new session for that.